So thank you, everyone. My name is Aljaz, and I work at Fusion for Energy. I'm not one of the developers of this tool, but our institution does support the team developing this tool with just different means. So from the administrative and also financial and so on, because it at the moment forms one of our key elements of the workflow for nuclear analysis. So just before jumping to the tool, I want to motivate a bit the development of the open source tools. So I want to mention a bit how the models for ITER developed throughout the years. So if you're not aware, the nuclear analysis for ITER, the models are based on the use of so-called ITER reference models. These are all models are based on the constructive solid geometry, or so-called CSG, and they provide a common framework just that allows you to carry out nuclear analysis in a consistent manner. They're developed, updated, and distributed throughout the community. And they work in a basic principle that if we want to study a specific area of the tokamak, we can just prepare a so-called universe with that detailed geometry, replace it in the reference model, and then run the calculation. So as you see, this was the model that was created 25 years ago. And then along the years, as you can see, these models were gaining a lot on the complexity. So we went from the 20-degree model to a 40-degree model, as you can see it here. We have the reflective boundary conditions on these sides, just to get the whole toroidal representation. So this was already in the 2011. Then, of course, again, almost 10 years later, in 2018 and 19, we got even more complex models. So this was a so-called C model, as you can see it here, and this was the NBI model, the 80-degree model, just representing the NBI sector, or the so-called irregular sector of the ITER machine. And then in 2020, there was a very significant release in terms of models. So we have published a paper in Nature Energy on the 360-degree Monte Carlo representation of the ITER tokamak. So this was a very, very complex work that basically meant, a detailed representation of all the machine study at that time. And also a few years later, Paolo Romano and his colleagues, they produced an OpenMC equivalent of this model, which I hope you can see here on this screen. So this is the OpenMC model of E-Light that we also used to benchmark OpenMC and to try to see how it performs when running so complex geometries. But of course, all the models that you have seen, so these were 450,000 cells, they were all created by almost a single software. So for all this, we have used so-called MCAM, SuperMC, or TopMC software. So this is a proprietary software that was free at that time for ITER application. And then we have tried in this years also tried to use different other methodologies like CAD, radiation transport on CAD models like DAG-MC or the unstructured mesh of MCNP, but we have discovered some significant challenges. At that time, the codes were quite not so well optimized, and it was difficult to mesh so gigantic models because, as I mentioned, the E-Light model, the 360-degree model, it features 450,000 solids or cells in MCNP or OpenMC. And also the problem was also when we had to calculate very detailed responses, like on the right, you can see a very specific geometry of one diagnostic system. When we had to calculate the nuclear heating of on the sensors, for example, of the system, it was basically impossible to get any reliable statistics using the unstructured meshes. So the only way was to get some good values using the CSG geometry, and then the structured mesh with which we were able to better manage the statistical errors by the size of the voxels. And at that time, of course, some free and open source alternatives to this MCAM and SuperMC or TOPMC existed, but of course they were less with less active development and maintenance, because this was basically driving the whole ITER analysis throughout the many years. Of course, you can imagine now that depending on one single tool in the key workflow for nuclear analysis can be quite worrying. We were worried, and also our colleagues from the UNET University, they were worried. So this has, of course, motivated a development of a new tool called GEOUNED, which the idea was to have to free an open source tool for CAD to CSG and reverse translation. As I mentioned, this was developed at UNED, the Spanish public university, and it's also an ITER supplier of nuclear analysis. And now in the recent years, they also collaborate with Fusion for Energy. This is the European domestic agency working on the ITER project, just trying to adapt this tool to a more production quality, to set up also the GitHub repository with the CI, with the documentation, and all the rest that comes with it, like also myself doing this presentation in front of you and trying to motivate your involvement or just trying out the tool. So now we have seen this tool was created just in time when the original developers of the MCAM, SuperMC, or TopMC actually started asking quite a lot of money for a license to work on the projects. For us, this was a significant problem because as an institution, it was difficult to justify payment of tens of thousands of euros to continue with the ongoing analysis. So for us, it was important to try to push some existing project like the GEOUNED to become better and also more easily available to all the other users around Europe and around the world at the end. So just if I can present now a bit of the GEOUNED. So this is programmed in Python 3. It's based on FreeCAD as interface for OpenCASCADE CAD engine, and both the FreeCAD and OpenCASCADE, they're open source and actively supported. Just the workflow of the tool basically works in a way that you load the files, which are usually the step files. Then you run the decomposition algorithm, which breaks down these step files into more basic convex solids. Then we do the conversion of these basic solids into Boolean expressions. And of course, the tool also has this automatic void generation, which creates negative or it fills up the space that was not explicitly represented in this in the CAD model. At the moment, this code, the GEOUNED code, supports MCNP, which is, of course, one of the which we also try to work on the most, but it's also able to translate OpenMC models, so both from the CAD to OpenMC description and also in reverse. But for the reverse, it has to have sort of MCNP-like description. So all the surfaces and cells, they have to be described using just the integers. It also supports Serpent and FITS, but these are significantly less tested, so we also don't have a lot of feedback on how well it performs and what kind of improvements we could add to this tool. So this tool also has quite handy this automatic model verification. So when we add the so-called simplified CAD model in step file with the material list where we have the material IDs, the densities, we throw this into GEOUNED, we produce MCNP or OpenMC deck, and then as a source that is created at the end, it creates sort of a tally with a list of cells that were created with the SD4 that populates with the volumes of the solids in CAD model. And then when you run this source, you can just quickly check if all the results of this tally are equal to 1. So when you see a larger deviation from 1, there might be 2 things. So 1, maybe you use the too low number of histories and you should sample it better, or there was maybe a problem in the translation and the MCNP volume does not correspond to the original CAD volume. So this is a very good way and quick way of just identifying that, confirming that the translation went well, or just identifying the issues with maybe specific solids in the translation. It also has, this is a very good feature, it's called enclosures, and it separates this tool from all the rest. There were, as I said, there were some free and open source options, but less maintained at the time, and also the proprietary software, but none of these had this option of enclosure. So what this basically allows us is that when we have to produce the void space, so all the rest that is not explicitly represented in CAD model, we can separate this void production per rooms. So this is very handy. For example, if you want to, like in this case, if you want to create a specific air cells for inside the different parts of the installation, or if we move to the next slide, it is also very handy in applications where you receive a very complex component, then you have to simplify. And but in those CAD models, in the generic CAD models that we usually receive, they don't model the liquids. So sometimes it's a very handy way of just preparing a specific void in the area where you should have, like in this case, the lithium lead, or maybe water. So this was not in the CAD model, but the code is able to specifically model all the voids in this, and you can just assign a material that you want, and this is the resulting model then. And I've tried it. This also works in OpenMC, so no problem there. So there is also, as I mentioned, the CSG to CAD conversion for MCNP. This was quite tested, but it also works for OpenMC. Just the example that you can see here is the one that I published some time ago on the OpenMC discussion in the forum. But as I said, one of the limitations, of course, is that the input that you want to translate has to be prepared in a MCNP-like way. So integers for cell and surfaces, and with that mentality. But what happens then is when you run the code, it takes the input deck and it produces a step file. When you open it, you will find inside solids separated by materials that were found in the input deck, and then also separation per cells. These are the cell numbers that were found in the input deck. All right. Then, as I said, it also has the CI in which we translate the solids. We also run the OpenMC to calculate just to calculate the volumes, and we compare them to CAD, so we can see that when we do a code change, that we don't actually break the functionality of this tool. So And we have also worked quite a lot on the documentation, but it's still a work in progress, as you can see it here. And then current work or future work is that we are working a lot on maintenance and improving the documentation. We're trying to significantly improve the decomposition logic, because at the moment it works like throwing solids into a blender and then trying to piece together these parts. But of course, we're also working on the parallelization of this decomposition, because each solid can be done by a specific thread. And our colleagues at the UK are also investigating a bit on substituting FreeCAD, because it's a very heavy dependency, by maybe a lighter, faster tools. So this tool can be downloaded at a link here. For any doubts, questions, suggestions, problems, whatever, you can contact just the main developers that you find the contacts here. These are also some of the papers that were written on GEOUNED, and this is then the GitHub repository also of our institution, because we tried to share also our tools that we use for nuclear analysis for ITER on GitHub and make them available to all the researchers. So that's everything. The last image is basically just one of the last models that was created for ITER, and just a bit of dimensions of this model. So this is close to 1 million solids or cells in the neutronics model. So thank you so much for everything, and of course, if you have any questions, please go ahead.
Excellent. Thank you, Aljaz. Yeah, feel free to clap, respond with your emoji of your choosing, do a little dance. Thanks so much. It's a great talk. It's a really useful tool. I've tried it out a couple of times myself. There's one question in the chat that if you wouldn't mind answering live, that would be awesome. Yeah. The question is, are there any current limitations on geometrical objects that can be represented and converted? And I had the same curiosity myself about how like higher order surfaces are handled in the tool. Okay, so at the moment we have so splines, these do not work at all. This is impossible because of course you cannot also represent them in neutronics codes like OpenMC or MCNP. We have a bit of challenge with torize. But this is again it's under progress. So we are able to make a translation with torize in the geometry, but the geometry in SpaceClim or in CAD processing tool has to be prepared in a specific way that the decomposition will work well. So that's the main challenge at the moment. So this is a very good question. Yeah, thank you.